Hello, everybody, and welcome to the first video of the year. We're going to get it popping right off with some terminology. So, we've got a bunch of different words right here that all mean stuff to us in geometry. Frequently, when we do these videos, I will ask you to pause the video, and I would encourage you to do so. That way, you can think ahead and try to figure some of this stuff out yourself. And then you can unpause and check with my responses to see how accurate your thinking was, if there's anything you need to change, or if you get a big atta boy or atta girl and mosey on along about your way. So, right off the bat, I would suggest that you try to pause the video and see if you can identify any of these terms in this image over here. Specifically, if you really want to do it right, try to use the proper notation. So, like, for example, when you go to write a point, we always use capital letters for points. So, like, if I was going to do point A, just a big capital A. Whereas if I was going to do a line, we'll talk more about it in a second, but you would write like BD with this little thing over the top. So, if you want to take a stab at it, I would highly suggest it. Go ahead and pause now and try to fill in some examples of these other terms. Did you do it? Did you pause the video and try on your own? Great job if you did. So, some of the examples, like I mentioned before, to write the name of a point or to write a specific point, you just use the capital letter that is at that point. So I listed A, B, C, dot, 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 because there's other ones, A, B, C, D, E, F. That's all we have. You could add more points on if you wanted, give them a letter and include that. But you always use capital letters when you're talking about points. With a line, you need 2 points because you need 2 points to make a line. If I just had 1 point like that, I could draw this line or that line or that line or that line. There's an infinite amount of points, lines that can go through 1 point. But as soon as I add a second point, it locks in that line. I can't move it anymore. It's stuck right at that spot. So you label it with 2 of the points on that line. If you happen to have more than 2 points, like here, I could use BA, AD, or BD. Those are all the same line in this picture. So sometimes you have multiple ways of naming the same line. But one of the important things is it has those arrowheads, 2 arrowheads on the top, which indicates that a line does in fact go on forever in both directions. It never stops. It just keeps going on and on and on and on, much like my videos. On the other hand, a segment is a part of a line that is cut between 2 points. So like line AC goes specifically from point A to point C. And sometimes that's all there is to it. Or sometimes like on BE, it goes from B to E. It does keep going further. But when I write it like this without the arrowheads, that means it stops at B and E. I'm not considering these parts of the line. I'm only considering this segment right here. So we'll talk a lot about line segments this year, and they are different than lines because lines go on forever. And kind of a mix between those is what's called a ray. A ray has one end point, so like CE, ends right here at C, but then it goes on forever in one direction. So like sun rays, that's where the term comes from, is that they start at the sun, right? The sun rays haven't been shooting across the universe forever. They come from the sun, but once they leave the sun, they keep going forever, which is kind of crazy to think about. Like when you see light from another star, that's a distant sun, and that light has traveled thousands, if not millions of years to get to your eyeball at that one instant right there. Sometimes stars you see are actually dead. They don't exist anymore, but it's taken so long for the light to get here. We still see them, even though they've exploded by now. But anyways, I digress. Circles have a little circle with a dot in the middle and the point at the middle. So I can't just use like point B. There is no circle B here. There is only circle A, because A is the point that is at the center, or at least I'm assuming for this video, that A is the center of this circle right there. Now, angles. Oh my gosh, do people mess up angles? Angles are made from 3 points. Again, kind of like a line needing 2 points. I can't make an angle just out of 1 or 2 points. I need a third point to draw a second line segment to. And that's what forms the angle. So you use those 3 points that make the angle to name the angle. So like BEC, goes from B to E to C. I can also name that same angle CEB, but it's important that E is in the middle because that's where the angle bends at. So it's not just angle E, because angle E could be this angle, it could be this angle, could be this angle, could be this angle. There's 4 different sides to point E where these lines go through it. So you need at least 3 points to name or to properly determine where an angle is. B to E to C clearly defines that angle right there. All right? And again, dot, 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 I have plenty of angles. ABE, ACE, ADF is the same as BDF, right? Because it still makes the same angle because I have 2 points on the same line right there. So we'll talk lots and lots and lots about angles, but please try to start getting that in your head right now. You cannot use 1 letter to name an angle. You need 3 letters or 3 points to name the angle. Parallel lines are when you have these vertical bars right here, shows parallel because, they look parallel, whereas perpendicular, lines that make a 90-degree angle, are shown with an upside down T, 2 lines that look perpendicular. And again, BE and DF, I use little line symbols above them to show they're parallel lines, not line segments. And I know that they're parallel because they're both perpendicular. They both make 90-degree angles here. So parallel means they run right next to each other forever. They never intersect, right? So if they're both perpendicular to a singular line, that means that they're parallel to each other because they're both 90 degrees to this, what's called a transversal. Again, we'll study much more about that later. I just wanted you to be familiar with this terminology of the vertical lines. And then, perpendicular is just when it makes a 90-degree angle. So BE, line BE is perpendicular to AD or BD, this line here. I could have also done DF is perpendicular to BD. So that's another example of perpendicular. All right, so now we're going to talk a little bit about a plane. A plane is a flat surface that contains a whole bunch of points. In fact, an infinite amount of points in any plane. You can't see them all because we're not going to sit here and draw an infinite amount of anything. But a plane is a flat surface. Like this table right here is a plane. It's a flat surface made up of an infinite amount of little spots. I could put an infinite amount of dots on this table, and it's all in the same plane. This piece of paper is a plane. It's actually a better example because just like on a plane, I can turn it, I can move. But once you identify 3 spots, kind of like the line, it locks it in. So a line needs 2 points to lock in. A plane needs 3 points to lock in. If you've ever been at sitting on a chair that's wobbly, it's because it probably has 4 legs. 4 legs don't have to be in the same plane. One leg could be shorter than the others, which is what makes it wobble. But if you ever sit on a stool, stools don't wobble because there's 3 of them and they'll settle into the floor, whatever angle the floor is at. So 3 points make a plane. So go ahead and maybe pause and see if you can think through. If you don't want to write in and worry about erasing, at least pause and think about these questions yourself, and then I'll go over them with you here in just a second. All right. So, which of the shown points appear to be contained in plane W? So again, plane W, this little cursive, by the way, they usually use like cursive letters, like kind of curly Q looking ones to represent planes. We don't work with planes, honestly, that much. It's just a fundamental idea that will come up from time to time, so I want to make sure you're familiar with it. But they kind of use a little cursive one. So that's plane W down here. And A, B, and C are the ones that are shown in plane W. Remember, a plane has an infinite amount of points. We've just highlighted points A, B, and C because they're part of this larger diagram here. So A, B, and C are the ones that are shown in plane W. There are actually 5 different planes shown here. So we've got plane W down here at the bottom. Plane ABC is the same as plane W, so I don't count that one because ABC is already inside of W. Kind of like I wouldn't count this part of the table right here as a table. It's part of the larger table, right? So like if I just draw this little table in the table, this is part of the larger plane. Does that make sense? I don't know, whatever. So we've got the flat one on the bottom. We've got this one over here on the left that has A, B, E, and F. We've got this one over here on the side that is E, B, C, and D. this one up here on the top, and then it's kind of hard to think about, but there is a backside to this as well. Oh, you can't see that. There's a backside to this figure as well that goes through F, D, C, and A. So it's 1, 2, 3, 4, 5 for the backside. So there are 5 different planes shown in this figure. I'll address that idea of shown in a second too. Name 4 points that are coplanar. So coplanar means in the same plane. So remember, you need 3 points to make a plane. You can have more than that. Again, just like W, every plane has an infinite amount of points in it. And in this picture, A, B, E, and F, so A, B, E, and F, this side over here, are all coplanar. B, C, D, and E, B, C, D, and E, this side over here, are all coplanar. And then on the back side, A, C, D, and F, A, C, D, and F would make another flat surface, a plane on the back side of that figure. F, E, and D are coplanar, but they're only 3 points. I asked for 4 points that are coplanar. So anyways, just trying to get you thinking about this idea of planes and kind of how they work. Are points F, B, and C coplanar? So when you first look at it, F, B, and C. Well, if I just have those 3 points right there, it doesn't really make one side to this shape that's shown. But again, you have to remember that a plane can be drawn through any 3 points. So even though it's not shown, I could make a plane that goes through those 3 points. So when it asks, are they coplanar? Do they lie in the same plane? Yes, any 3 points can always be coplanar. It's only when you add a 4th point that it locks it in. Again, kind of like that example of the line. 1 point has an infinite amount of lines. 2 points have an infinite amount of planes. It's when you add that 2nd point on a line or the 3rd point on a plane that it really locks it into place so that you can't move it anymore. And again, that's why I specifically set up here how many different planes are shown. There's an infinite amount of planes we could draw here. There's 5 of them that are shown, right? And I don't know, whatever. Planes, that's a thing. You'll probably never hear me talk about them again. Moving on. Write 2 different names for each angle shown in the diagram. I'll go ahead and do the first because you might not know what I mean yet by that. So angle 2. Well, there's a 2 that's over here that designates in this picture. I numbered all the angles. So this is angle 2. And 2 different ways you can name that angle would be M to P to R. See how M, P, R? If I go from point M to point P to R, that carves out the same angle. And likewise, I kind of mentioned it already, but you can reverse that R to P to M. Again, I'm really just trying to get you comfortable with this way of writing angles because very rarely will we ever have them numbered. Like we're going to work with things that have tons and tons and tons of angles in them. You wouldn't want to have to sit there and number them all the time. So this notation is going to be very important for you to understand and to be able to use fluently this year. So go ahead and pause, try for angle 8, and then what happens when you combine angles 4 and 5? What would you name this combined angle right there? All right, so these actually had a few more ways that you could write the angle. So angle 8, this one right here, could be written as M to O to P, M to O to P. Of course, you could also reverse it and go POM, but I felt like that was boring because there's another point on the line. So I could also name it MOR or ROM. So that's what I put and reverse order here. These are just like squiggly brackets. They don't mean anything in geometry. They're just me showing you that I'm talking about this stuff. I could reverse these orders. I might as well go ahead and write them in POM and MOR. Just trying to be lazy right in the reverse order thing. But yeah, there's actually way more than 2 here because there's more than 1 point on each line. So M to O to P is the same angle as M to O to R, which is the same angle as R to O to M or P to O to M. So I could write that out in any of those orders. And then angle 4 and 5, kind of same idea. PMN or NMP carves out that larger angle, not just 5. If I was looking at 5, it'd be NMO. But I'm not. I'm looking at the bigger angle combined between those two. NMP or QMN. NMQ. So I could write that angle a couple of different ways as well. Please ask if you don't understand what I'm talking about. This is so important. Like planes, kind of not. Angles, oh my gosh, we do so much work with angles this year. Make sure you understand how to write an angle. It looks embarrassing and it undermines all of your work the rest of the year when you just don't understand how to write a series of points in an angle like that. So, all right. Same picture, but different questions here. Hopefully you know what acute and obtuse angles are. I'm assuming you know what right angles are. Maybe not straight and vertical, but go ahead and pause now and see if you can identify at least one example of each of those from that picture to the right. You can use the numbers if you want. You don't have to you should use the letters, but I'm probably going to use the numbers just because we're already at 15 minutes. So go ahead and pause and try to identify each of these in the picture over here. All right, acute angles, hopefully you know, just means less than 90 degrees, whereas obtuse is more than 90. And a right angle is 90 degrees. So there's tons of acute angles in here. Less than 90, less than 90, less than 90, less than 90. Like almost all of these are acute angles. A couple obtuse ones, angle 2 and angle 8. So angle 2 is this big boy right here, is definitely over 90 degrees. And I also included OPQ because I didn't have a number, but O to P to Q, I could name that angle with the 3 points. So those are both obtuse or larger than 90 degrees. There aren't any right angles. So I put this in here just to see if anyone would look and be like, that looks like 90 degrees. If it is not marked with that little square in the corner, then it is not 90. We've got to start trying to get away from the habit of saying, it looks like that's going to get you in trouble this year in geometry if you just try to base it off of it looks like, rather than looking for information that you actually know. So that would mark a 90 degree or a right angle right there. But there aren't any marked here, so don't just assume. Now, straight angles also are called supplementary angles. They mean they add up to 180. So angle 7 and angle 8 would be an example of a straight angle because they add up to a straight line. They're two angles that even though they're not marked, we don't know the angles of each to know they add to 180. I can see with those arrowheads that this is a line, and if I'm going to continue along that line, that has to form a 180 degree angle right there. So 7 and 8 would be called a straight angle, and this is another one. Vertical angles are angles formed on opposite sides of intersecting lines. So like angles 1 and 3 here, see how two lines intersect, or even line segments, it works as well. If I just had little pieces like that, these angles are called vertical angles, or also these angles are called vertical angles. The top and bottom or the sides vertical, even though that's horizontal, they're also called vertical angles. Vertical angles just mean they're across from each other. They're formed from intersecting lines. And something we know about vertical angles is they're always equal. So I actually know that angle 1 equals angle 3 here. So we'll talk a lot more about that in this chapter. All right. Name an angle or an angle pair that satisfies each condition. So kind of similar to up here, but just going through some more vocab you're going to need for this chapter. So go ahead and pause and see if you can work through and identify some of these angles or angle pairs that satisfy that terminology. All right. So the angle that forms a linear pair with ABC. So A to B to C is right here. And the line that we have to work off of is this one right here, technically line segment. But we know that because that continues on straight like that, this has to be a 180 degree angle. So ABC would be a linear pair with GBC or CBG. This is the angle that forms a linear pair with that one because they make a line. That's what the root of linear is, line. Those two angles form a straight line. Complementary, so we didn't have this up in the top part, but complementary adds to 90 degrees. Supplementary, as I mentioned before, adds to 180. And I always remember those alphabetically. C, then S, 90, then 180. C comes before S, 90 comes before 180. So complementary adds to 90, supplementary adds to 180. So the one that's complementary with FGC, well, we know this is a 90 degree angle. This is FGC right here. So then FGH, this part over here, would be the complementary part, or HGF. FGH or HGF is the same angle. Supplementary, two angles that are supplementary to BCD. So BCD is this one right here. So BCD could be supplementary this way, or it could also be supplementary this way. See how this forms a straight line, but then this also forms a straight line this way. So this is supplementary, and this is supplementary. There's two different ways to go with BCD to make a straight line. So angle DCF, DCF, this one right here, would be complementary to BCD, DCF, or BCG, this angle over here is complementary to BCD, right there. Finally, two obtuse vertical angles whose vertex is at C. So here's point C. That's the vertex, is the point where the line bends. Obtuse, bigger than 90, vertical, across from each other. So right here, these would be the ones that are vertical, obtuse angles that have a vertex at C. So BCG and DCF. Same answers as before. These are also obtuse vertical angles whose vertex is at C. Dang, that's got some terminology in it. Okay. Couple more. Keep practicing with this terminology, and then we'll actually do a little bit of arithmetic right here at the end. So pause next to last time. We'll pause one more time after this and see if you can identify whether or not each of those statements can be assumed from the figure. Remember, if things aren't marked, you don't want to assume them. Go ahead and pause and try to figure out whether or not you can assume each of those things. Right meow. All right. So, first one you might have thought was easy. No. We do not know that this right here is a 90-degree angle. You might be like, but it looks pretty close. Not good enough. It could be 90.001 degrees, not 90 degrees. You don't know because it doesn't have the little 90-degree mark, so you can't assume it. If it had that little 90-degree mark right there, absolutely they're complementary, but it doesn't. So you can't assume. You got to start breaking that habit. So we do not know that that's a 90-degree angle, therefore we do not know that these add to 90 degrees. The second one, though, it definitely forms a straight line. Look at SRQ, this angle right here, and QRP, this angle right here. See how there's arrowheads on both sides right there? If that wasn't a straight line, then it would not be a linear pair. But since this makes a line right here, then we can say that yes, those two angles form a linear pair because we know that there is line SP. And our MQN and PQR vertical angles, MQN, this angle right here, and PQR right here. Yes, those are vertical angles. We don't know what the number is. We don't know how many degrees each of these angles are, but we know that they're equal. They are vertical angles because they're formed by NR and MP intersecting. So the opposite angles from intersecting lines are always equal, and we call them vertical angles. Woo! All right, let's do a little bit of arithmetic and wrap this bad boy up. So we know that this big angle here is 90 degrees, and we know this part up there is represented by some expression. 2 times some number plus 8 is how many degrees we have up here. Down below, we know that one. That's exactly 30 degrees down here. And together, those two have to add up. This stuff plus 30 have to add up to 90 because they form a complementary angle. It's marked, they add to 90. So we can actually just solve this like a good old equation. I just put those parentheses, I totally didn't need them. 2x plus 38, combining like terms, equals 90. Subtract 38 and divide by 2, and that will solve for x. Solve for the variable or variables in each of the following diagrams. So 90 minus 38 would be what? 52. So 52, 2x equals 52. And then if I divide by 2, x would be 26. Yeah. All right, last time. Pause the video and see if you can work out what you think each of these variables are. There's only an x in number 11. There's an x, y, and z in number 12. Take your time. Work through them. All right, I went back through and rewrote that a little neater. So you can see the 2x plus 8 plus 30 equals 90, solved out for 26. Over here, this is a linear pair. So this adds up to 180. So this stuff, this plus this has to equal 180. So I subtract the 108 and I put the variables together. So I have 6x equals 72, 180 minus 108. Divide by 6, x would be 12. Now, over here, we've got a couple things going on. Right off the bat, if you look closely, you can see that CF and DA intersect, making this a 20-degree angle, and angle Y, the Y variable, is a vertical angle with that 20. So that means we know automatically vertical angles are equal. Y equals 20. Then from there, it's a little hard to see where the way it printed, but that does have a 90-degree mark there. So I know that these are perpendicular to each other, which means this side is also perpendicular. So these are complementary. 20 plus x has to be 90, so if I subtract the 20, x is 70. Then once I know that part, once I found the y, see how this expression right here also uses a y? So I took that 20 that I found from here and plugged it in for y. If y is 20 right there, every y in the problem has to be 20 because it's the same variable. So I have 5 times 20, because y is 20, plus 10. So it's a 110-degree angle. We know that y is a 20-degree angle, and all 3 of these parts have to add up to 180 because they make a linear combination, a linear pair right there. So this is 110, 20, and z. Z plus 110 plus 20 has to be 180. If I solve for z, I find that z is 50. If I lost you a little bit on these parts, please reach out. You can email me, talk to Mr. Sheridan, whatever you need to do. Just take your time, work through your Khan Academy sections, and let me know how I can help.